So we finished learning about alkanes. Our next kind of organic compounds are the alkenes. An alkene is simply an alkane that contains a double bond within the carbon-carbon chain. They are also referred to as unsaturated hydrocarbons. What that means is that when you form a double bond, you have to take off some of the hydrogens that were originally on the compound. Take a look at this compound that I've drawn here. This is propane. If I were to add just one more bond between the C's and C's, I have to remember that all the carbons, they can only accommodate 4 bonds total. So what that means is if I want to make another bond between those 2 carbons, I have to lose some of the H's. And this is what we mean by unsaturation. We have to take off some of the H's that were originally on the compound. The number of H's that I have to lose in order to accommodate a double bond is 2, one from each of the carbons receiving that additional bond. I'm just going to rebalance my structure here to make it a little bit more accurate. Why am I doing that? Well, because this carbon here has 3 attachments, and when a molecule or when a central atom has 3 attachments, it's a trigonoplanar structure with 120 degrees with for the bond angles. So drawing it like this is just a little bit more accurate. Let's do the condensed structure. It would be a CH3 first for this grouping here, followed by a CH for this grouping here, followed by a CH2 CH2 for this grouping here. If I were to do the line diagram, it would be like this for 1, 2 carbons. Here's the 3rd carbon, and then we draw a double for where that double bond is. Alkenes are said to have isomers as well, and to understand where the isomers come from, let's first investigate alkanes. Here are 2 alkane molecules I've built with our molecular model set, and I want you to take a look at these and assess whether the 2 molecules I have are indeed the same compound. One has 2 special parts. We'll just call them A and B, branch A and branch B, with the red and blue ball. 2 branches on the first molecule are pointing in the same direction. The 2 special branches on the second molecule are pointing in opposite directions. Are these the same molecules? Now, they actually are the same molecule. Single bonds in alkanes are highly flexible. There's only one pair of electrons sharing to make that bond the center, and as such, the bond length is quite long and flexible so that the bond can rotate. So this structure here is the same as this structure here, the one that I built a second ago. Now let's look at what happens when we have an alkene. Here I have 2 alkenes that I've built, each with a carbon-carbon double in the center. Are these 2 the same compounds? And the answer here is no. When you have a double bond, double bonds are made when 4 electrons are shared between 2 atoms. And the bond length is considerably shorter, as we learned in Unit 8, and they are resulting in a rigid bond. This double bond cannot rotate. So for an alkene, we always have 2 isomers that are possible. One where the carbon chain is a U shape or a boat shape, and one where the carbon chain is a zigzag shape or a long chair kind of shape. Let's write down what we just discussed in our notes here. Let's draw the alkane that we first looked at, CCHH, and I'm going to put on a branch A, let's call it branch A, and a branch B. Now this molecule that I've drawn here would be the same as if I were to draw it like this, with the A over here and the B over here, which is also the same as if I were to draw it like this. And this is because single bonds are flexible, they're quite long, and they can rotate. So if we rotate that alkane round and round, you'll get three structures that may seem different, but they are actually the same compound. Alkenes, in comparison, cannot do that. Double bonds cannot rotate. And so every alkene that we have has two isomers, the cis and the trans isomer. Here's what that would look like. A cis isomer will have special branches facing the same side of that double bond. So if we analyze the structure with a plane across the double, we see that the branch A and branch B are on the same side of that. Same side is called cis. Okay? Same side cis, same side cis. If the two branches, special features of that alkene, is on opposite sides of the double bond, so if we are looking at the double bond across here, we see that A and B are on opposite side of that double. That is called the trans isomer, the transversal. Okay? If we were to draw that in a line diagram, the cis isomer would look like a boat, and the trans isomer would look like a little lawn chair. Let's look at some examples to see if we can identify whether what we're looking at is a cis or a trans. The first one here, if we draw the double bond axis, we see that there are two branches, an ethyl and a methyl, and those two are both pointing upwards. They're on the same side of that double bond, so this is the cis isomer. The next one here, we have again two branches, that F fluoro and an ethyl group. Now this one, they are located on opposite sides of that double bond, so this will be what we call a trans isomer. The next example is a line diagram. Again, if you draw a little plane across that double, you can see that the branches over here and over here are on opposite sides of that double, making this also a trans isomer, a lawn chair shape. The next one, here is our double bond plane. We have two branches. They are both pointing on the same side of that double. So this is another example of a cis. It looks like a boat. Remember that line diagrams don't show you what the H's are, but if I were to draw them in, they would be right here, and both the H's are pointing on the same side, making this also a cis isomer. Some alkenes have more than one double bond. Here is one. This would be the trans. We see that long chair shape. Here is another one, and this would be the cis isomer, and we see the boat shape. If you see a condensed structure, if I were to ask you where that double bond is, it is located right here, and you can tell that the double is right there because we have two H's here that are just singles instead of the usual CH2, CH2. So that's telling you that there is unsaturation at that point. Unsaturation meaning loss of H's. So that's where the double is. Hey, here's a tidbit. Now that you know what unsaturated means, now you know what the difference is between saturated fat and unsaturated fat. Unsaturated fat has a double bond in the structure, and saturated fat is full of H's all around the carbon backbone. So there you go. Alright, back to this condensed structure here. This one, because it's not showing you the actual structure, it's just showing you the condensed formula. You cannot tell whether it's cis or trans, so for these guys, we simply cannot tell. Okay. Now let's go and learn how to name alkenes. Let's do a simple one first. 3, 4, right there. When we name alkenes, the main parent chain must contain that double bond, and that double bond takes priority. Now, what priority means is that when you go ahead and number the chain, we have to number it in a way such that the double bond receives the lowest number. So if we go from left to right, this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, and that double bond is going to first appear at carbon 4. If we go the opposite way, 1, 2, 3, 4, 5, 6, 7, 8, 9, the double bond first appears at carbon 5. So we are going to go with the first numbering system from left to right so that the first appearance of the double occurs at carbon 4. This structure is a trans. We see that long chair motif, the zigzaggedy pattern. So we write trans first. Then we write where the double bond is located, and it's on 4 for this one, trans 4. Then we name the parent chain, which is a non-name chain, but instead of saying non-name, we're going to change that to non-nene for alkenes. Isn't that clever? So clever. Alright, let's do another one. Here we go. This again is a long chair shape, so we would call that a trans. Where is that double located? Well, if we go from the left, it is going to be on carbon 3. If we go from the right, it is also going to be on carbon 3. Either way, doesn't matter. It's going to be trans 3 hexene. Alright, let's go do something more difficult. Let's add some branches. Okay. Alright, the longest chain here is going to be 1, 2, 3, 4, 5, 6, and 7. Going from the left so that the double bond gets 3, which is the lowest we can achieve on this structure. We write sister trans first. This is another trans. It's a zigzag shape. Then what we have to do is, this is the part where we put in the branches. So we have a branch right here, and that's a 2 carbon branch. That's an ethyl. It is on carbon 5, so we write 5 ethyl. After we do the branches, then we finish off with the double. It is on carbon 3. There are 7 carbons, so this is 3 heptene. Please try this one on your own and see if you get it. You can pause the video always and then resume once you think you have the answer. Okay. Alright, this double bond here, this is a cis. We see that boat structure with carbons pointing on the both upwards. Let's fix that here. Go. This is a cis. The longest chain. Did you manage to find the longest chain? Let's see. The longest chain is actually 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the longest chain there. It's a 9er. Okay. So there's a cis. We have a ethyl group. Where is it? Where is that ethyl group? It is right over here, the ethyl group. Cis 5 ethyl. Our next one is going to be 4 propyl. Our double is located on carbon 2. There are 9 carbons in total, making this non-nene. Did you get that right? I'm going to label this now, see if you can double check your answer here. This is carbon 1, 2, 3. Whoops. 3. 4 is here. 5, 6, 7, 8, and 9. We have a ethyl branch here at 5. We have a propyl branch here at 4. Some of you may wonder, why did we start 1 from over there and not over here? Why didn't we go 1, 2, 3 from this direction? Well, if we did that, this part would be considered a branch, and we have no way of naming a branch that contains a double bond. Whenever you choose the main chain for alkenes, always choose the path that contains the double bond. Okay? The main parent chain, the longest consecutive chain, must have the double bond within. Alright, let's finish up with a challenge question here. This molecule is quite small. You might be wondering, why is that a challenge? Sometimes it's tricky to decide whether it's cis or trans. If we look at the structure, we see that there is a boat shape, and that's this one going like this. Here's the boat shape. But we also have a lawn chair shape, and that's this one here. So is this guy cis or trans? How do we know which to choose? It seems like it's both. When you get a case like this, we always choose the two branches across the double that are the largest. So we're comparing the two largest branches. So that would make it this one with this one. So this structure is trans. So this is going to be trans. We're going to number them from this side so that our double bond and our methyl branch both receive the lowest number, because the rule is lowest number set if possible. So this is trans, 3 methyl, 3 hexene. Okay. There are compounds, alkene compounds that contain more than one double, and we have a naming system for that as well. So let's take a look at an example of that. Here's an alkene with two doubles. Same rules apply. We're going to number them off, giving the doubles the lowest number set, lowest possible that we can. Our first double that we encounter at 2 is a cis. So we're going to write cis. Then to do the other one, we're just going to put a comma. Our second one is a trans. Hopefully you saw that, the long chair shape. Then we write down our numbers. It's going to be 2, 4, where they first appear. And this is a 7 carbon chain. This is going to be heptene, except there's two doubles. So we use our prefixes just like we use them for our two branches of the same type. This is heptadiene. The prefix di is appearing right before the E and E to say that there's two of the double bonds. Okay, those prefixes always appear right before the thing that they apply to. Our final example, let's do a tough one here. I'm going to give you a very long chain here. Let's put a double here, here, and here, and just for fun, let's put a little branch at the end there. Okay, same rules apply. We are going to number this, giving our double bonds the lowest numbers possible. So we're going from the right. Here we go. The first double that we encounter is a cis. The second one that we encounter is a trans. The third one we encounter is also a trans. Now before we write about the double bonds, we have to address the branches. We have a branch at position 8, so it's 8 methyl. Alright, now we put in our numbers for our doubles, and that's 2, 4, and 6. This is a 10 carbon chain, so it's going to be deca. A space here, deca. 3, the prefix of 3 is tri, decatriene. And that's how you name alkenes. Goo out.